In this second part of the program, we'll go over how we can reverse the rotation of AC motors, the different deceleration methods used for stopping an AC motor, and how the speed of an AC motor can be controlled. We'll also go over in detail how to troubleshoot single-phase and three-phase AC motors. So let's start by looking at how we perform the reversal of AC motors.
In many industrial applications, there is a need to reverse the rotation of an AC motor. We know that by exchanging two of the leads in a three-phase motor and by exchanging the leads of the start winding in a single-phase motor, this change in rotation can be achieved. The methods employed use drum switches and manual or magnetic starters.
Let's start by first looking at the reversal of single-phase motors with the drum switch. Drum switches have 6 standard terminal connections, and we know that a single-phase motor only needs to have the start winding terminals exchanged in order to reverse the motor rotation. As can be seen, there is a jumper added between terminals 3 and 5. When the switch is in forward, the start and run windings both have the same L1 and L2 power lines connected. When the switch is changed to reverse, the run winding still has the same connections, while the start winding has its L1 and L2 lines reversed. Remember that clockwise and counterclockwise motor rotation is determined by looking at the motor shaft from the end opposite where the load is connected to the shaft. Reversing a single-phase motor requires 2 contactors to switch the 2 lines going to the motor. Reversing these 2 lines is done very similarly with manual and magnetic starters. The only difference is that, in the magnetic, the coil activates the power contacts as opposed to a manual switch. As seen in the wiring diagram, when the motor is in forward, L1 is directed to the T1 and T5 terminals of the run and start windings, while the L2 is routed to the T4 and T8. When in the reversal state, only the terminals 5 and 8 are reversed. The control circuit to reverse a single-phase motor is similar to DC and three-phase motors. For example, this compelling circuit with mechanical interlock will make the motor go forward when the forward push button is pressed. Once the stop is pressed, it will be allowed to reverse. When the motor has 3 phases, L1, L2, and L3, connected to the motor terminals T1, T2, and T3, the motor will rotate in the forward direction. By switching 2 of the phases going into the motor terminals, let's say we switch L1 and L3, the motor will rotate in the opposite direction, or in the reverse direction. We could have switched L1 and L2, or L2 and L3 to their respective switch terminals, and the results would have been the same. The drum switch provides you with a mechanism of making the line switches to the motor terminals easy to implement and operate. In the off position, the drum switch makes no connection to the motor, so there is no power to energize the motor, and it is therefore in a stop position. The drum switch provides a chart which denotes the contacts inside the drum which will be making contacts at the reverse and forward positions. In the off position, no contacts are made, so no power is passed to the motor. In the forward position, contacts 1 and 2, 3 and 4, and 5 and 6 are connected, and in the reverse 1 and 3, 2 and 4, and 5 and 6. As can be seen, if we are switching L1 and L3, we would wire L2 to drum switch contact number 5. Connection 6 goes to T2. Note that the number 5 and 6 contact connections don't change in the drum switch for either forward or reverse positions. L1 can go to contact number 1 and L3 to contact number 4. In the forward position, the forward contact segments 1 and 2, 3 and 4, and 5 and 6 make connection, thus switching L1, L2, and L3 to T1, T2, and T3 respectively. When the drum switch is placed in the reverse position, the contact segments 1 and 3, 2 and 4, and 5 and 6 will be making connection, thus connecting L1, L2, and L3 to T3, T2, and T1, respectively, for a reverse motor rotation. This is illustrated by the heavy lines making contact on the screen.
Note that the L2 connection to T2 does not change in either the forward or reverse positions. The reversal of manual and magnetic starters is basically done in the same manner. Let's take the magnetic starter. Two contactors are used in the reversing starter, while one set of overload relays is used. In the forward direction, as you can see, the F contacts will close as controlled by this non-compelling circuit. As soon as forward is pressed, L1, L2, and L3 are routed to T1, T2, and T3. Once reverse is pressed, the R contactor will be energized, and the L1 and L3 lines will be redirected to T3 and T1 respectively, therefore changing the rotation of the motor. This circuit provides double interlocking to prevent the motor from going forward and reverse at the same time. One is mechanical, provided by the push buttons, while the other one is electrical, provided by the auxiliary forward and reverse contacts. With a slight modification, this control circuit allows the three-phase motor to jog in the forward and reverse direction. When in run, it will act as a forward-reverse control with interlocking, while in the jog position, the motor will go forward every time the forward push button is pressed. The same applies for the reverse jog. Every time reverse is pushed, the motor will rotate in the opposite direction. Deceleration circuits are extremely important when a motor needs to be brought to a stop quickly. In AC motor controls, deceleration involves electromechanical friction brakes, plugging circuits, and electric braking. Deceleration of an AC motor to a stop can also be accomplished with electromechanical brakes, of which the most commonly used is the friction brake. The friction brake is solenoid operated and basically works like an automobile brake system. It is connected between two of the phases of the motor, or, depending on the brake, between one phase, let's say L1, and neutral. The operation is the same. If the motor is started, power will be available at the solenoid, and the brake shoes will be pulled by the solenoid action, thus removing friction from the drum. When power is removed to the motor circuit, the brake solenoid is de-energized and the brake spring is allowed to apply full force to the brake shoes so that maximum friction is created and the motor is brought to a stop. The amount of spring pressure is adjustable through a screw. If set to maximum pressure, the brake will make the stop very quickly as soon as power is removed. If the pressure is reduced, the motor may be allowed to coast slightly before coming to a stop. During preventive maintenance, the shoes of the brake should be inspected to ensure that they are not worn out, and replaced if necessary. If you need to select a friction brake, it will be necessary to choose it by taking into account the amount of torque of your motor. To obtain this value, you can use the equation of torque equal to the horsepower of the motor times the constant 5,252 divided by the speed of the RPMs at which the motor is operating. The value of the torque will be in foot-pounds, and the brake's torque should be equal to or greater than this value. For example, a 100 horsepower motor running at 1,000 RPMs will need a brake of at least 525.2 foot-pounds. Plugging in an AC motor circuit is accomplished by using plugging switches to bring the motor to a quick stop by changing the direction of rotation. The plugging switch, as we know, closes in the forward or reverse position once the direction speed setting of the rotation is achieved. In a simple plugging like this, the plugging switch can be used to implement a quick stop by reversing the motor once the stop signal has been pressed. Let's see. When start is pushed, the motor will start in the forward direction, and the plugging switch's forward contacts will close and set up the reverse motor to wait for the normally closed forward interlock to be back to its normal state. This will occur as soon as we press the stop push button, which will reset the forward starter coil. At this time, the reverse starter will be energized because there is continuity provided by the plugging switch forward contact, which is still closed by the centrifugal force due to the rotation. The reverse starter will be disconnected as soon as the rotation in the plugging switch slows down close to zero speed. This type of deceleration can also be used in single-phase AC motors, except in those motors which utilize centrifugal switches. This plugging circuit operates in a similar manner, but allows plugging a motor to stop from either direction. A slight variation of the plugging circuit is the anti-plugging. This circuit allows reversal of direction once the rotation slows down to a predetermined speed. If the motor is running in the forward direction and stop is pressed, the reverse will not be allowed until the forward rotation slows enough to close the forward contacts in the switch. At this point, the reverse can take place. A braking method which differs from the ones we have looked at is the electric braking. This method employs DC current which is applied to the stationary winding of an AC motor after its voltage has been removed. Electric braking provides an excellent way to provide braking capabilities to circuits of all types, including high speed and those with high inertia loads. Maintenance of these braking systems is minimal since no moving parts come in contact physically during braking. Electric braking uses a principle similar to that of dynamic braking used in DC motors. Once an AC motor is turned off, the DC voltage applied creates a magnetic field in the stator which doesn't change polarity, and once it interacts with the rotor, the rotation is stopped quickly. This type of braking can be applied to both single-phase and three-phase motors. In a single phase, the plus and minus terminals of the braking voltage are switched to the running and starting windings, while for the three-phase motor, the connection is made to two of the line phases. The control circuit is fairly basic. When the motor is started, the timer is turned on and its off-delay contacts close. The M1 contacts provide interlock to prevent the brake contacts from turning on the DC power. As soon as the motor is stopped, the electric brake will be applied by means of the brake contacts closing and providing the DC power to the motor. This DC voltage, as you can see, is provided by a bridge rectifier. When the off-delay elapses, the normally timed open contacts of the timer will reset back to their original open state, thus releasing the electric brake. As we know, the synchronous speed of an AC motor can be regulated by either changing the number of poles in the motor or by varying the frequency of the voltage to the motor. To implement the speed control by changing the number of poles requires special three-phase wound motors called multispeed motors. When implementing the speed control changing the frequency of the voltage, a drive is used, and it is generally referred to as a variable frequency speed drive. Let's first take a look at multi-speed motors. We know that by removing poles from the motor, we would increase the speed of the motor. However, this also means that the motor provides less horsepower when these poles are removed. There are many multi-speed motor lead connections that are selected depending on the torque and the horsepower requirements for the application. These connection arrangements conform to NEMA standards. Multi-speed motors are broken down into three classifications, which are constant torque, constant horsepower, and variable torque. The constant torque has its horsepower variable. The constant horsepower has the torque variable, and the variable torque also has the horsepower variable. Some motors provide two speeds, low and high, while others provide four speeds, such as low, second, third, and high, just like the gears in our cars. Multi-speed motors provide the necessary wiring to allow for proper connection of the poles at the stator. These connections are controlled by using circuit interlockings in the control circuit and in the power circuit, so that the motor is not run at low and high speeds at the same time. These circuits may look similar to the forward-reverse controls we've seen before. For example, this circuit allows the operator to start the motor at either of the two speeds, but he must stop the motor before changing speed. We can easily modify this circuit so that the operator could change the speed from low to high without stopping. Many applications may require low-speed compelling, which means that the motor must start at a low speed and then be allowed to accelerate to the high speed when required. In this circuit, CR1-1 contacts prevent the high-speed contactor from being energized unless coil CR1 is on. This can occur only if the low speed is first selected. Some accelerating circuits, like this one, utilize a timer on delay to bring the motor to high speed once the low-speed push button has been pressed. This circuit gives the motor and driven equipment a definite time to accelerate from low to high speed. If the operator passes the high speed first, the circuit will start the motor at the low speed and then increase it to the high speed. Bear in mind that the speed of these motors could have been controlled automatically by pilot devices. For example, if the selector switch is an auto, the pilot devices would control the activation of the low or high speed. As you can see, this circuit allows the motor transition to turn from low to high speed, but not from high to low in either the auto or hand positions. The variable speed drive controls the speed of the motor by providing a supply of phase voltage to the motor at a different frequency. This AC drive is similar to the DC drive, except that here it changes frequency instead of voltage to control the speed. When a variable speed drive is used, the speed of the motor can be controlled from 0 to full speed very smoothly, also providing soft starts. Any three-phase squirrel cage motor can be used as long as the horsepower is large enough to move the load and that it doesn't exceed the drive size limitations. These drives also provide capabilities to start a motor with just enough torque to cause movement of the load. This is the so-called breakaway torque. One of the most popular methods used in AC drives is with the use of an inverter. In an inverter drive system, three-phase power is received and rectified to a DC voltage and inverted back to AC at a different frequency. The inverter generally uses SCRs, which are controlled to fire on and off at selected times to create the new AC waveform signal at a new frequency. This waveform may not look exactly like the original power signal, but as long as it has a sinusoidal characteristic, it will be sufficient to create a magnetic field to rotate the motor. There are 3 of these signals created by the inverter spaced 120 degrees apart. The frequency in the drive is generally controlled from 0 to 60 hertz, although some drive may provide from 0 to 200 or more hertz, depending on the design of the drive and the application. The higher the frequency, the faster the speed of the motor. Just as in the case of the DC motors, AC motors present problems if they are not able to either turn the shaft when power is applied or if they have continuous overheating problems while running. In either of these 2 cases, we must find the problem, isolate it, and fix it so that the motor is not damaged. You can troubleshoot three-phase and single-phase AC motors in a very similar manner. However, since there are few parts that differ from one another, there are just a few differences in the tests performed. As we mentioned earlier, you will troubleshoot the motors using 2 methods of attack. One if the motor does not turn on with power, and the other if there is power and it overheats or runs in a poor manner. The troubleshooting methods and procedures explained here are listed in the order they may occur, from the most likely you're to find to the least likely. Before we go into troubleshooting a motor with power, let's review a troubleshooting procedure for a motor with power removed to the motor but available at the starter. We'll assume that the control circuit that drives the motor has already been through troubleshooting and is operating correctly, thus providing voltage to the starter's coil. During troubleshooting of the power circuit at the starter, you must exercise extreme caution because these circuits can carry large voltages and currents capable of causing severe harm to personnel if not very cautious. For simplicity during the procedure of checking the power circuit, let's remove the sections which correspond to the ladder diagram control circuit. With the starter on, we first start by checking with the meter for voltage presence in the L1, L2, and L3 lines by measuring across each, from L1 to L2, from L2 to L3, and L3 to L1. We should be able to see a very close voltage reading among all 3. This line voltage should also be within 10% of our motor's nameplate voltage rating to avoid a high or low voltage problem. If there is no power in either one or all of the lines, we need to trace back our troubleshooting to the supply voltage and fuses that feed this motor circuit. If, while checking the power, you discover that there is no voltage and that one or more of the fuses is blown after the disconnect, you can assume that a potential short has occurred in the circuit or in the motor itself. If the power feed has a protected branch circuit for the control circuit, a short in this area can be eliminated because it is protected by its own fuses. Note, however, that this control circuit will have no power. If the fuses are blown, they need to be replaced before power can be applied again. If they blow again, then a short circuit is present in the power circuit. If the fuses do not blow, then the most likely place the short has occurred is in the motor itself. You need to check the windings of the motor for a ground connection with a meter set for a continuity test. It is possible that the stator winding in a three-phase or the run or start winding in a single phase is touching the frame, which is grounded and therefore short-circuiting the whole system. This condition is known as a grounded winding. If there is correct power in the three phases, then the next thing you need to test are the contacts of the starter. To do this, we check from L1 to the load side of the L2 contactor to check for the contacts at L2. The voltage should be the same as from L1 to L2 in the supply side. Next, we check for the contacts in line 3 by placing one side of the meter to the supply L1 and the other side to the load side of the contacts at L3. You should read again the same line voltage. To check the contacts at L1, then we need to check from the load side of the contacts on L1 to either the supply of L2 or L3. Here, you should see again the same line voltage. If you don't see the proper voltage in all lines, something is wrong with one or more of the contacts. If this is the case, you must remove power to the motor circuit and check the contacts by removing the contact elements from the starter. They may be making poor contact if there is contact chattering, or they may be dirty. If they are dirty, you should clean them and test them again. If they are damaged, you'll need to replace them with another set of the same rating. If the contacts are working properly and supplying the proper voltages, then you should check the overloads. In fact, in a motor control circuit, if the motor was running and stops, the first thing that you should check is to visually see if the overloads have been tripped. This is usually available at the starter, where an overload trip indicator can be visible. If this is the case, you should wait a couple of minutes and reset the overloads and start the motor. If the overloads keep tripping, you may have a problem with the motor and load, which should be checked, or the heaters may be sized too small, thus making the motor trip the overloads frequently. The overloads must be sized according to the motor's manufacturer and the starter's manufacturer specifications and the rules of Article 430 of the NEC. When troubleshooting the overloads, you should take into consideration the ambient temperature at the starter and at the motor. If the ambient temperature at the starter is higher than the temperature at the motor, the heater should be selected with the next higher rating. If the ambient temperature at the controller is lower than the temperature at the motor, the heater should be selected with the next lower rating.
These temperature considerations will help balance the heat created by an overload current so that the heater melts at the correct temperature, taking into consideration the effect of the ambient temperature.
If an overload has occurred, you also need to inspect the starter's contacts with power off to check for possible contact welding. If there is welding due to the extreme current, you need to replace the contacts. To check voltage continuity from the contacts through the overloads to the terminals of the motor, you should place one side of the meter on L1 and the other to the load side of the overload L2. If there is voltage, the heaters are okay. The same check is done for line 3. We measure from L1 on the load side of the overload on line 3, and if we see the proper line voltage, then the overloads are good. To check the overloads in L1, we can take a voltage reading from L3 to the load side of the overloads. Again, if there is the proper line voltage, then the overloads are okay. If any of these voltage readings that were used to check the overloads is not correct, you need to remove power and check the overload heaters for an open condition, which can prevent it from conducting current to the motor. If the voltage is present at the terminals of the starter that go to the motor, you need to check and make sure that the wire connections are making good contact and that these are not loose, so that we can eliminate the wiring from the starter to the motor as a problem.
After we have checked for power to the terminals of the motor, we can assume that the power circuit is in good working order and that we are faced with the most common problem that occurs in a plant, which is that the motor does not start when power has been applied to it.
If the motor has voltage at its terminals and has a humming sound, it indicates that it is drawing current and has a problem which needs further investigation. If it does not hum,
It indicates that it is not drawing current, so there is a possible open in its windings. You could use a clamp-on meter to measure and record the current being drawn by the motor. If you suspect an open in its windings, then remove the power to the motor and test its winding with a meter set to a resistance reading to see if you measure infinity resistance between its leads. If so, the motor has an open and should be removed and repaired. If the motor is drawing current, it will make a humming noise. This tells us that there is a problem with one of its coils or one of its phase voltages. You should check the line voltage again to make sure that one phase has not been lost and the motor is trying to start single phasing. If all voltages are present at the motor leads, then you need to test to see which one is not drawing current. With a clamp-on meter, test each line and document their current readings. Once you find the line which is not pulling current, you'll need to test for continuity in the winding.
Before you start the test, make sure that your motor has not tripped an internal thermal switch, which may be available in some larger motors.
These switches may be connected in series with a control circuit to detect an internal overheating condition of the motor. If this is the case, then you should wait for the motor to cool off before you resume checking.
If your motor had internal thermal switches that are constantly tripping, the motor may be creating extreme amounts of internal heat, which requires attention, or it may be exceeding operational temperatures.
These can include problems with ball bearings or faulty coils in the motor. Additionally, you should check for a possible mechanical bind on the load, or to see if the load is out of alignment. Both conditions could cause an increase in current that generates heat, which, in combination with a hot ambient temperature, could add to make the internal temperature switch trip. To test for continuity in the windings, you'll need to remove power to the motor and disconnect the wires to the motor from the starter. With meter set for ohms reading, we begin the test. If you read an infinity resistance measurement, the coil is open and needs to be removed and repaired. For a dual voltage delta motor, you have to test the three circuits that form the delta voltage. For instance, you would put the meter leads between T4 and T1 and see if there is continuity, and between T1 and T9 to check also for continuity. The same applies to other circuits. If it is a single voltage delta motor, you will simply measure from T1 to T2 and T1 to T3 and 2 to T3 for continuity. In a dual voltage Y motor, the continuity test is performed in a similar manner, except that you'll have 4 circuits instead of 3, as in the delta motor's case. Here, you'll measure for continuity between T1 and T4, T2 and T5, T3 and T6, and then from T7 to T8, T8 to T9, and T7 to T9. If any of these windings show infinity resistance, then there is an open in that winding. If the motor is a single voltage Y, then the measurement of continuity will be done between T1 and T2, T2 and T3, and T1 and T3. This method can also be used when testing for shorted windings, except that you would measure each of the terminals in the delta or Y motor to a ground, for example, to the grounded frame of the motor. If there is continuity, then there will be a short in the motor. If a single-phase motor has power applied at its terminals, it will be humming, indicating that it is drawing current. Since there is only one phase voltage at its terminals, it can be assumed that all its control circuits are working properly because the starter coil is maintaining the motor energized. The hum indicates a problem with the start or the run windings, since the motor will not start if one of them is not working. The probable cause can be an open in one of the windings. To check for an open, we would disconnect power to the motor and test the leads T1 to T4 for continuity in the run winding. If there is an infinity resistance reading in the meter, then there is an open in the winding. Otherwise, the coil is good. Next, we need to check the start winding from lead T5 to T8. When testing the start winding for continuity, if the motor is a single-phase capacitor motor, you will need to use a jumper and jump or bypass the capacitor so that a continuity test can be made. If there is an open, you should first check the centrifugal switch for an open or malfunction. You need to measure with a meter across the switch for continuity. If the switch is good, then the open would be in the winding. If the switch is not good, you need to replace it and test the winding again to ensure proper rewiring and that the winding itself does not also have an open. If any of the windings are open, the motor would need to be replaced. If the windings are both good, the potential problem may lie on the shaft or on a binding load, thus not allowing the motor to start. Remove the load from the shaft and start the motor. If the shaft does not rotate, then you need to check the bearings. If the shaft rotates when started, you need to check the load's bearings and make sure that the load capacity is not being exceeded for the motor.
You may find, while doing routine preventive maintenance or general equipment checkouts during normal operations, that a motor is not running properly and is overheating.
In a three-phase motor, this could be caused by a loss of a phase due to open wires in the power circuit, an open in the motor windings, or a blown fuse in the power circuit. In fact, a phase loss can happen after a storm, which has knocked out a line coming into the plant, or even by lightning striking a utilities transformer bank. If the motor is overheating due to these conditions, it will not start if it is turned off. In fact, it should be turned off as soon as possible, because otherwise it will burn out. Then you can investigate the problem further. The three-phase motor can also be overheating if the bearings are not properly lubricated in the motor or at the load side. If there is a low voltage across the three phases, it could also cause overheating of the motor, and it should be turned off until the under-voltage problem is corrected at the plant. Other reasons that will cause a motor to overheat include improper field wiring, a loose coil in the motor, or if the load is too large for the motor application. If the field wiring for a three-phase dual-voltage motor is connected for the wrong voltage, it will translate into an overheating problem. You should make sure that the motor's terminals are properly connected for the dual-voltage operation. If a single-phase motor develops a heat problem after a start, you should check to see that the centrifugal switch is disengaging the start winding once the motor speed has reached 75% of full speed. If the start winding is not taken out, it will create heat. Like in the case of a three-phase, a low voltage in the plant can also create an increase in current intake by the single-phase motor, thus also resulting in an increase in temperature. Lack of proper lubrication in the motor bearings or at the load can also contribute to overheating. If the motor has not been properly sized, being either too small or too large for the load can also create overheating in the motor.
In this module, we have covered the methods and circuits used for controlling the operation of AC motors. These included the reversing of motor direction and the full and reduced voltage starts. We have also gone through the important procedures you should have present when troubleshooting AC motor controls. Bear in mind that having a proper method of troubleshooting as well as recording and maintaining good record keeping will help you immensely in solving problems and bringing the equipment back online.